We've seen a ton of equilibrium reactions and worked with equilibriums in regular and acid and base equations. Now, let's take a moment to think back to the first semester of chemistry. We considered ionic equations and learned that some things are soluble and some are not. We had this fancy table to memorize. Now is when we get to see the reality behind that table. The reality is that solubility is an equilibrium process. The more solute dissolved into a solution, the less likely it is to continue dissolving. At some point, it will reach a critical stage where there is so much dissolved in the solution that no more could dissolve. This point is called the saturation point. However, in solutions well below the saturation point, the ability of a compound to dissolve is governed by its solubility product constant, or Ksp. Let's look at an ionic solubility equation. Here we have the ionic compound sodium chloride. It can dissociate in water, giving us sodium and chloride ions. The Ksp is written using the same logic that an equilibrium constant is. However, it is important to remember that a solid isn't part of an equilibrium equation, only gases and aqueous substances. Remember your polyatomic ions. These are also part of this system. For calcium sulfate, these would be the resulting ions, and this would be the Ksp. For slightly soluble ionic compounds, Ksp is determined from a compound's molar solubility. That is a measure of the moles of dissolved solute in a saturated solution. In this example, calcium fluorite can dissociate into 1 calcium and 2 fluoride ions. If we add just enough calcium fluorite, or any ion, till the solution cannot dissolve anymore, that is what we call a saturated solution. Remember that this is an equilibrium, which means if we add more past the saturation point, the rate of precipitation equals the rate of dissociation, so we won't get any more dissociated product. For calcium fluorite, the concentrations of calcium ions in such a solution would be 2.15 times 10 to the minus 4 molar. In order to calculate the Ksp, we need the concentration of fluoride ions as well. What's great about this is we can use our knowledge of molar ratios to figure this out. The concentration of calcium ions is 2 to 1 with fluoride, so we can set up a conversion. Boom! Now we just put those values into our Ksp equation and solve for Ksp. That's not too bad. We can also use an ice table to calculate the molar solubility from the Ksp. We can ask what the molar solubility of lead-2 sulfate would be. First, we need to look up the Ksp. It's 6.3 times 10 to the negative 7. Then, we can set up an ice table. Remember that solids don't count. Now, we set the system equal to the Ksp and solve for x as we have done before, only in a slightly easier way. We can also solve problems that involve the common ion effect. In this situation, we have barium carbonate being added to a solution that already contains 1.4 times 10 to the minus 3 molar dissolved sodium carbonate. How much will this affect the solubility of barium carbonate? This is just like an equilibrium with a non-zero starting condition for products. We can make an ice table and include the already present concentration of carbonate. The Ksp of barium carbonate is 5.0 times 10 to the minus 9. This allows us to write the Ksp equation. Then, we just solve for x, which is the molar solubility of barium. Go ahead and work through Unit 6 in your workbook. Also, take some time to consider the conceptual ramifications of solubility equilibriums. Next time, we're going to leave equilibriums behind and look at thermodynamics. We will consider the laws of thermodynamics and how they interact to explain a variety of chemical and physical properties.